This video gives you a basic understanding of load flow studies and how to formulate the static load flow equations. Load flow studies are also known as power flow studies, and they form an important part of power system analysis. These studies are necessary for planning and operation of the power system, for economic scheduling and control of an existing system, as well as planning its future expansion. The load flow studies gives steady state solution of the power system network. The problem consists of determining the magnitude and phase angle of voltages at each bus and the active and reactive power flow in each of the transmission line together with the power at the reference bus. The information obtained from the load flow solution is necessary for continuous monitoring of the operating state of the power system, and also important to analyze the new operating state in case the load on the system has increased or the new transmission facilities has been created. Let us now formulate the static load flow equations. So let us consider the part of this network, and the two nodes has been shown in the power system, ith node and the jth node, or we can call them ith bus or the jth bus, where the different components are connected. The bus power is denoted as SI. Similarly, at the jth bus we can write the bus power as J, and SI is the bus power, which is also the complex bus power. So if you look at the node I, at the node I we can see that the generation is facilities provided, that is the generators are connected at the ith node, and these generators are feeding power into the network through the transmission line to the load which is connected at the jth bus. So we can write the power SI, which is known as the bus power or the complex bus power. SI is SJI minus SDI, where SGI is the complex power of the generators, and this SGI is also written as PGI plus JQGI because this is a apparent power, so it will be having two components, the real and reactive components. And similarly, the complex bus power SI can also be written in terms of the two components PI plus JQI. The load is also represented in terms of power, and we can write the load power as SDI. Again, SDI is the apparent power of the load, and it can again be broken down into two components, that is the real load demand denoted as PDI plus the reactive load demand denoted as QDI. So the apparent power S is having the two components, active demand and the reactive demand for the load which is connected at the jth bus. Here SGI representing the complex power which is produced by the generator and injected into the system, and SDI is representing the complex power which is delivered to the load, and therefore this will result in a net injection at a bus denoted by SI, which is the complex bus power. In power system, powers are known rather than current, so the resulting equations for the load flow will be in terms of power, and that's why we also call them power flow equations. Usually we represent a system by a single line diagram, and a three-phase system is balanced system, so it can be represented by a single phase network. Equation 1 represents the complex power which is injected at the ith bus by the source. So we are representing the complex power, apparent power SI is equal to PI plus JQI, which is the real power component and reactive power component at the ith bus. This can also be written as VI into conjugate of the current II conjugate. However, it is easy to work with the current I instead of its conjugate. So we will be taking the complex conjugate of the equation 1 again, and this will give us the equation number 2. Substitute the expression of the bus current I in the equation number 2, and this will give us the equation number 3, where we can separate the real and imaginary part to write the separate expressions for the real power and the reactive power denoted by equation number 4. Now by applying the Kirchhoff's current law at the ith bus and converting the impedances to admittances which are connected between the ith and the jth bus, we can write an equation for the bus currents denoted by equation number 2. Let us define the voltage at ith and jth nodes and the admittance between the ith and the jth nodes Vij in the polar form, and substitute these in the equation number 3 to obtain equation number 5, and rearrange the terms to obtain the equation number 6. Again, we can separate the real and imaginary parts from the equation number 6 in order to write the equations for the real power Pi and the reactive power Qi denoted by the equation number 7. The equation thus obtained are known as the static load flow equation. In short, we can also write them as SLFE. So if you look at this equation for the n bus system, these are the total 2n non-linear algebraic power flow equations. And what does it indicates that at each bus there are 4 variables. Thus the total will be 4n variables for an n bus system. The 4 variables are, if we look at the equation 7, we can clearly see the 4 variables denoted at any of the ith node will be Pi, Qi, Vi and delta I. So these are the 4 variables which are defined at the bus. And usually in a power system, out of these 4 variables, 2 variables are usually specified. So the other 2 variables can be found by solving the power flow equations. That is the equation number 7 for Pi and Qi. If we look at the equation 7, we can see that there is a presence of cos and sine terms in this equation which makes them non-linear, and in order to solve these equations we require the iterative techniques like Gauss-Seidel method or the Newton-Raphson method. In a power system, the buses are generally classified into 3 types: generator bus, load bus and the slack bus. The buses where the generators are connected are known as the generator buses. These buses are also known as voltage controlled buses or the regulated buses. We will be writing the designation of this bus as a PV bus because out of the 4 quantities that we have seen in the load flow equations, 2 quantities are specified for each of the bus. So for a generator bus, the quantities which are specified is the voltage magnitude and the power, that is Pi and Vi are specified at the generator bus, which you can see in the table. So for this generator bus, also known as PV bus, the unknown quantities are, or the values of these Qi and delta I are unknown, so that will be evaluated when we solve the load flow equations. So in a system we can see that out of all the buses which are there, 15% of the buses are usually the regulated buses or the PV buses or the generator buses. So at the generator buses, the real power and voltage magnitude are specified, and the phase angle of the voltages and the reactive power needs to be determined. Also there is a limit on the values of the reactive power is specified at the generator buses. Now why do we call these buses as the PV buses? Because the power generation of such buses can be controlled through a prime mover, while the terminal voltage is controlled through the generator excitation. So keeping the input power constant through the turbine governor control and keeping the bus voltage constant using automatic voltage regulator, we can specify constant Pi and Vi for these buses, and that's why we refer these buses as PV buses. Also you can note that the reactive power which is supplied by the generator Qgi depends on the system configuration and cannot be specified in advance. Therefore we have to find the unknown angle delta I of the bus voltage. As you can see in the line diagram, the node 1 where the generator is connected will be termed as the generator bus or the PV bus. Also in the line diagram, if you look at the node 2, at the node 2 the load is connected, and such type of bus is designated as the load bus, also known as PQ bus, because at this node the parameters of the load, that is P and Q, are specified, and the voltage magnitude at this bus and its angle is not known, that is it needs to be determined. So we can say that at these buses the active and reactive power is specified, and the magnitude and the phase angle of the bus voltage is unknown. So these buses are called PQ buses, and in a system we can see around 80 to 85% of the buses are PQ buses. Apart from PV bus and PQ bus, there is one bus in the system which is known as the slack bus or swing bus, and this bus is taken as a reference where the magnitude and phase angle of the voltages are specified, and this bus makes up the difference between the scheduled loads and the generated power that are caused by the losses in the network. So at this bus we can see that the quantities which are specified as Vi and delta I, and the unknown quantities are Pi and Qi. Usually this bus is numbered 1 for the load flow studies, and this bus will set the angular reference for all other buses. So when we solve this in the load flow studies, we usually take the angle of this bus as 0 degrees. We can also represent the static load flow equation in terms of the components of admittance. Now admittance Yij between the ith and the jth node can be written as terms of its component as Gij minus Jbij, where G indicates the conductance and B indicates the susceptance between the ith and the jth nodes. Substituting this expression for Yij into the expression for the complex power at the ith bus, that is Pi minus Jqi, we can reformulate the load flow equation in terms of these components. As you can see that now we are getting the equations Pi and Qi. By separating the real and imaginary parts, we can write the expression for real power and reactive power in terms of the components of the admittance. In order to solve the static load flow equations, we require the iterative techniques like Gauss-Seidel and Newton-Raphson method. So keep watching.